This is a brief introduction to adaptive optics. Motivation for adaptive optics really started out in the astronomical community. The problem was that people were imaging through telescopes on the ground and trying to see details, find details of stars in remote galaxies. And as the light from the galaxies passed through the atmosphere, there's turbulence in the atmosphere, little particles scattering and interfering with the direction of the rays, scattering them a little bit. And that means even though you'd have a really great telescope over here. In fact, there was a kind of addition to the telescope, the unwanted turbulence of the atmosphere, that turned the image into a fuzzy blob. So as a result, even the largest ground-based telescopes really were limited by this. Making the telescope bigger and better didn't really help because the atmosphere was such a problem. So as an example, if you couldn't solve this just by averaging. If you took a long exposure image of a star, it would just blur out like this, and if you took lots of short image exposures, each one would look like this, and the pattern that you'd get moment to moment would depend on the turbulence in the atmosphere. The perfect image, if you really had a diffraction limited telescope, might be this small. So it's really quite a big effect. So if it weren't for the turbulence, you'd get this, but with the turbulence and a short exposure you get this, and a long exposure you get that. So in fact, adaptive optics solves this problem. So this is an example of a particular telescope in Albuquerque, New Mexico, and you can see that you can resolve with adaptive optics two stars over here, and without adaptive optics it just forms this big blur. So what's the idea? So we're going to now, instead of applying this to astronomy, we're going to apply the same principles of adaptive optics. I'm going to explain them, but with respect to trying to see into the human eye. And the human eye, you also have a kind of unwanted refraction errors, kind of imperfections of the eye itself. It's not the atmosphere that's causing the problems in the imaging, but it's the eye itself. So let's characterize that. Suppose you actually had a perfect eye, one that was just a diffraction limited system, and you had a point of light at the back of the eye. Maybe you'd get that point of light there by just illuminating that point with a laser, so it just goes through a small part of the lens and ends up in the back of the eye. You have a point on the back of the eye, and light is scattering from the back of the eye out through the cornean lens over here. And you then, if it's a perfect eye, then from the perfect optics of the eye, then this point over here will bend all the rays so that they're parallel, like this, collimated. You'll take it through a diffraction limited lens, and you'll form a nice tight spot over here, and you'll get these little point spread function. That's the airy disk of the circular aperture of your eye. But your eye is not perfect. Your eye has aberrations, and that means when this point comes out of the optics of your eye, the rays, instead of being perfectly collimated, end up going at just slightly wrong angles like this. And one way to characterize this, a description that we use to talk about these the rays going at different angles, is actually to draw the little perpendicular like this to each one of these rays and put a smooth curve like that. And that little smooth curve that's perpendicular to each one of these rays as it heads out of the eye, that's called the wavefront coming out of the eye. And over here in the good eye, where everything's perfect, that wavefront is in this case is a plane. Over here, it's aberrated. It's not perfect at all. It deviates from the plane. So these are the wavefront aberrations of the eye as you're coming out here. And what you'd really like to know to be able to image better over here is, what is this wavefront aberration? Because if you knew it, you could correct for it. So how do you measure a wavefront aberration? Okay, so here's the situation in a perfect eye again. You've got a point of light. Maybe somehow you get a point of light in the back of the retina and scattering back out. If it were perfect, the wavefront would come out over here. And if it were perfect, you could put a whole little array of little lenses called a lenslet array, or a lens array, but a lenslet array if they're really little lenses. And as the light comes out through there and it's captured, each lenslet, since the ray is coming in right through the middle, will head straight along, and to the extent that there are rays coming up and down through the aperture of this, they'll all be converged. It's like they're coming from infinity, so they'll come down to the focal distance, the focal plane of this lens, and then one over here to this lens, and so forth. And what you get at the back on this measurement array could be CCD, could be CMOS. If you had a perfect aberration-free reflection from the eye, you'd get a set of points that are nicely equally spaced like this. Now, if you have an aberration like this, an aberrated wavefront like this, then in fact the rays coming from this region over here, instead of coming straight like this, they're kind of coming at a bit of an angle, and they'll end up being imaged. In this case, you can see the wavefront is indicating that they're angled this way. They'll come down a little bit, and they'll end up forming an image off the center axis down over here. Or over here, they're angled up a little bit. They'll form an image up the axis, just right over there. So depending on the wavefront aberration, on how the wavefront is curved this way or this way, the spot that you measure underneath each one of these lenslets tells you something about the local angle of that wavefront aberration. So the difference between the center, the line right through the center of the lens back to the imager, and where the spot is actually formed, tells you about the angle of the rays as they head towards this lens over here. So this is the delta x's over here are a way for you to measure the wavefront error. And a device like this lenslet array, is called either a Hartmann-Shack or Shack-Hartmann wavefront sensor, and it measures the image imperfections, the wavefront aberrations coming out of a lens like this. So this is a picture of a wavefront sensor, of a Shack-Hartmann wavefront sensor, and the data appear as these dots over here. And if depending on if you have a good or bad focus, I guess I'm not exactly sure, but I guess the blue dots are where a perfect array would form, and the red dots are displaced from it a little bit. And so there's from this you can go from all these little deltas, you can go and make in 2 dimensions a measurement of the wavefront aberration of the particular system that's being measured over here. Okay, so that's how you get the wavefront aberration. Now you'd like to correct the wavefront aberration, because when light comes out of here and the wavefront is aberrated, that means you can't really see. And remember, the point was you wanted to be able to see the stars and have them be in tight focus. In this case, you want to be able to see a picture right at the back of the eye and have it be in a tight focus. So what you really want to do is compensate for this wavefront aberration. That's kind of the goal. And so once again, just imagine here's a system that we started out for measuring it. You can sort of see it this way. We put in, let's say, a very thin laser beam that comes in just through the center of the optics and forms an image over here. That point is scattered back towards the pupil, the cornea and the lens. It comes out aberrated like this. Now, I probably should make this. If this were flat over here, just a straight mirror, just flat, the rays would come here and come down here to the wavefront sensor. And they'd come down to the wavefront sensor, and we'd see what the deviations are, and that would measure the wavefront aberration. But in this case, we've already made one measurement. We know what it is. And so what we're going to do is we're going to take this mirror and turn it into a curvy thing like this that'll compensate, so that when the rays come over here, they're going to be the wavefront is going to be transformed by this mirror, and this mirror is it's called a deformable or adaptive mirror, and it's just got these little pistons pumping it back and forth, and it's going to be pumped back and moved back and forth in such a way as to actually compensate for the wavefront aberration of the lens over here, and after it bounces off of that, if we check it through here, it's going to be nice and straight, and therefore when we send it through this lens, we're going to get a really high resolution image that's only going to be limited by diffraction. The wavefront aberration is going to be compensated for by the mirror, and that's going to give us a really great picture of the region right in where that spot covers, right in the back of the eye over there. Okay? So the adaptive mirror is adjusted to compensate for the wavefront aberration so that we can form a very high image at the back of the eye over there. And of course, if we move the spot around in the back of the eye, we can get a very sharp picture of some little region all around in the back over there. So this is one of the earliest rigs. This is a picture over here of Dave Williams, who's in his lab where a lot of this early work happened. And Austin Roeder, who's down the road at Berkeley, worked with Dave and has developed a lot of new technology for, just building this up. It's gotten better and better over the years, and this is for imaging using adaptive optics in order to image the back of the eye. Here's the deformable mirror. Here's the camera that does the imaging. Here's the Shack-Hartman wavefront sensor and so forth. And this is what things looked like over that back in the day. This is what computers used to look like. So these adaptive optics really improve the point spread function that you can get from the back of the eye quite a bit. In some eyes, if you put in a point of light, this is when it's scattered back out from the retina towards that retinal imaging camera. By the time you're done, you just get nothing but just flat kind of a thing. And when you turn on the adaptive optics system to try to correct for the wavefront aberrations, you get this nice tight point spread function, which greatly enhances your ability to measure the to see the back of the eye. So what does it look like? Well, without adaptive optics, here's a single image, and with adaptive optics, here's a single image. And if you average a bunch of times, you get sharp images like this. It's not here. This is a good case to average. You can go and make a much nicer, a really rather nice picture, and get a crisp look at all the individual photoreceptors at the back of the living human eye. And there's a scale bar. This is about 50 microns in this image. You can also use these methods to not only see the cones, but by cleverly adjusting the wavelength of light that you put in and testing things about how much light is scattered back, you can actually make estimates of which type of cone there is at each location. And that was first done by Austin Roeder and Dave Williams and others in a paper in 1999. And these were the first time that anybody could look into the human eye and make an estimate of the positions of the individual types of cones within the retina of a living human eye. It's a really cool measurement.